Okay, students, welcome. In today's class, we will look at supervised learning viewed as an optimization. In the Unit 2, under multi-layer perceptron, we have covered the topics that is batch learning, online learning, backpropagation, SEN and its role in online learning, generalization, approximation function, cross-validation, complexity regularization, and network pruning. The two topics left under the Unit 2 are supervised learning viewed as an optimization and nonlinear filtering. Today we'll look at some basic introduction to the supervised learning viewed as an optimization. I'll not be able to complete. In the next class I'll complete. Under this one we will be looking at two optimization algorithms, that is conjugate uh, gradient method and quasi-Newton method. This is the objectives of this topic. We have to learn these two optimization methods. Uh, we'll start like the supervised learning viewed as an optimization. First, we'll look at the concept of what is machine learning. The major goal of The major goal of training the machine learning algorithm is to minimize the degree of error between the predicted output and the true output. The input will be given and then we have to predict the output. For that, we will be constructing the neural network model actually, which is going to have the input nodes, and then in between we are going to have the hidden layer with the hidden neurons, and output it will be having. That is, neural network is going to act as a function which is going to help us to map between the input and then the output. But objective is what actually, when this neural network learns something, it should predict the output so that the error difference between the predicted output and the actual output is very less. That is what we have to do. That is, yeah, optimization is measured through a loss or a cost function, which is typically a way of defining the difference between the predicted and the actual value of the data. Machine learning models aim to minimize the loss, that is the error, or lower the gap between the prediction and reality of the output data. Iterative optimizations will mean that machine learning models become more accurate at predicting an output or classifying. That is, when we start this neural network to train, initially we'll start with some weight values actually for W1, W2 up to Wn, if there are n weights are there. We get some error actually, that is between the actual and then the predicted. Later what we will do is, like, we update these weights so that in the next iteration this error becomes further less actually. That is, here optimization is what we have to find the optimal values of the weights so that my error is going to get reduced. But we cannot do that in one iteration. It has to be done over a number of epochs or number of iterations actually. Therefore, it becomes an optimization. That is, supervised learning is viewed as an optimization. And as we want to learn the weights of the neural network so that our error is going to get minimized over the iterations during the training period. Therefore, supervised learning is not just weight updating. That is, we are not blindly updating the weights. It is a structured optimization problem on a non-linear error surface. That is, we have to find the optimized weights on the error surface, but we'll understand what is this non-linear error surfaces. That is, error surfaces in neural networks will become non-linear. That is, here in the diagram you can see, for example, say in the neural network, I have to have two weights, W1 and W2. That is the X axis, this is X1 axis, and this is X2 axis, and this is, say, the Z axis, and this is the error axis. And now what we will try to do, we will try to find the weights for the W1 and then W2 in such a way that the error goes down. That is, we should come to this point somewhere where we can find the optimal value for the W1 and the W2. That is, if my error surface is like a smooth bowl actually, I know that if I start here, I can roll down and then I can come to this point. Or if I start here, I can roll down and then come to this particular point. Because my aim is to come to this particular minimum point. Because I should find the minimum error. Because my z-axis is the error and W1 and W2 are the weights. I can roll down and then come down actually. But usually, yeah, the error surfaces when we have to map the input to the output, and when we have to minimize error, our error surfaces will not be a smooth bowl like what you are seeing here. Our error surfaces will be like ups and downs will be there. That is this the z axis. If we take it as an error, it will be there actually. When the error surfaces are like this, say for example, if my error function goes like this and then jumps like this, and this is y-axis is my weights, as x-axis is my weights, and my y-axis is my error. That is for this one, that is if I take this one, this will be my minimum point. That is, if I take further down this one, and this is slightly above actually, if I take this one, my objective is to find this one. Obviously, if initially if I would have started my weight here, I know I can roll down and then come back here actually. But I don't know, I'll start randomly with some weights actually. Therefore, if I would have started the weight value here, I will start here, I'll roll down, and then I will get stuck here and assume that if I go above, it is increasing. The error is getting increasing instead of getting decreased. Therefore, I'll stuck and then I'll stay back here. But the final objective was we should find the global minimum, which was here actually. What is the point we are trying to understand here is that is in the when we take the neural networks and when we are trying to learn the mapping between the input and then the output, our error surface will not be a linear, it will be a non-linear. Because of this non-linearity, when I have to learn this minimum value, I find the global minimum, it becomes a challenge actually, because it is not the two weights also. For example, when you have taken 10 weights are there, and your 10 weights are moving in different directions, and you have to catch them and make the values of the 10 weights in such a way that I will reach the global minimum. Therefore, the error surfaces in the neural network will be non-linear because we'll be using the non-linear activation functions, and also multiple layers and multiple weights will be there. That is, summary of this slide is supervised learning is not about just only updating the weights. It is about optimization problem where we have to find the global minimum in the non-linear error surfaces. For a neural networks, the error surface will be non-linear for sure. Therefore, up to now, what we have seen in the class is supervised learning may be explained as adjusting the weights using backpropagation, because we have done that one. When I have to update the new weights, what we did, Wn plus 1 will be Wn, and then the theta, and then we took the derivative of the error function with respect to the weights what we have studied until now. And if it was a gradient descent, we went in a negative direction by putting the minus here actually. And what we did, whenever we used to update the weight, we used to update this weight Wn plus 1 with the Wn, and then the updated weight is this one. And we used to try to reduce the error epoch by epoch over the iteration. But here, when we have to view the supervised learning as an optimization problem, the view changes actually. That is, training a neural network is treated as a numerical optimization problem. It is not just updating the weight actually. when we update this weight, we have to reduce the error actually, and that is the optimization we have to achieve actually. For training a neural network is treated as a numerical optimization problem. The neural network is the function because we will be having the number of hidden layers and hidden nodes with the weights. And the weights are going to act as a variables, and the surface error is the surface actually. And the learning is searching for the minimum of that surface. That is, in this particular surface, I should find where the minimum is going to occur, and then I have to identify what will be our suitable weights. That is what is being optimized. What I said, the quantity being optimized is the average error over the training data. This error depends on all weights together. Because of the nonlinear activation function, the error surface becomes nonlinear, high dimensional, and not a simple. Therefore, it becomes a challenge actually for us to find the global minimum or the local minimum when we have a non-linear error surface and we are treating it as an optimization problem. And therefore, we need the advanced optimization methods. The advanced optimization methods, what are the optimization methods which we can use is the gradient descent, conjugate gradient descent, and quasi, or nowadays when we use this Adam optimizer. Most of the time when you build the deep learning models, will go with the Adam. That is, optimizers are used to find the optimal values of the weights in the network so that our error function is error value is reduced actually. But the difficulty comes because the error surface is non-linear. If the error surface was linear, then we didn't had any difficulty. Now, when we have to find the optimal weights with the aim of the objective to keep in reducing the error or finding the global minimum, the error surface is non-linear, therefore the difficulty comes. Therefore, we'll see. Now, we'll look at like what we had with the gradient descent and then why we have to go with the conjugate gradient. Gradient descent is the central building block of the lots of the gradient-based optimization algorithms, including the conjugate gradient descent, because this gradient descent becomes a basic block for the conjugate gradient also, but the conjugate gradient overcomes the disadvantages of the gradient. The basic idea behind the gradient descent is to take a step in the direction negative of the gradient at each iteration. That is, if I take my error surface is a linear smooth, say this is my weight actually, which is going in the x-axis, and the y-axis is the error. Now, when I start here, and if I, what is my aim? I should find the value which is going to giving the bill. That is, when we start here, we have to move down actually. That is, we have to go against the gradient. But that is, we have to keep increasing the weight value here. But if I start here, I know that I should once again go against the gradient, but I should keep decreasing the weight values, because if I find the slope here, that is, it will be a positive, but have to come down actually. But here, if I find the slope, it is a that is, it is less than 0 actually, then I should decrease, because if I have -5, then I should decrease it by -4. But here in this case, if I have here 5, I should come down in the sense I should once again decrease. Here it is, sorry, here it is increasing, -5 plus 1 actually, it becomes -4. But here 5 minus 4, 5 minus 1 becomes 4 actually. That is, we will go against the opposite direction of the gradient. That is, in the gradient descent, that is, if f of x, that is input output mapping, that is, you have a d input vectors are there which we have to map to the output. That is, if there are 4 nodes in the input neural network and then 2 nodes are this one, then it is a mapping of 4 to 2. And this f of x is the loss function actually that we wish to minimize. That is, our aim is to reduce the error. Given the current estimate, that is, we know some weight values, that is, say this currently we know W, or else I will connect it to the we have connected the neural network gradient descent with respect to the weight vector. Say currently I know I have learned the weight vectors at the tth iteration, and I should know what is a weight vector at the t plus 1 t plus 1 iteration. Then what we said, it will be that is theta, the learning rate, multiplied by the negative of the gradient, where we find the derivative of the error function with respect to the weights what we have learned until now actually. That is how we used to update, because that also we have seen in the perceptron convergence theorem also. We used to update the weights like this. But here, what is the objective actually? That is, if I have learned the WT weights earlier, now I am learning WT plus 1 weight. But when you learn this one and when you try to find the difference, the absolute difference, the error should be reduced actually. Because earlier, if it was epsilon plus 1 error was there, now you should bring it to a error which is less than epsilon, because when I update the weights, the error should not get increased, because our objective is what? We have to reduce the error actually. Therefore, when we update our weights, actually, our objective is to reduce the error by somewhat compared to the previous. Now, when we take this gradient descent, what is the problem that we have is, this gradient descent actually ignores the curvatures, because if I go with like a smooth ball like this, got it? It knows that is it has to come down here and then it has to come down here, or if it has started, no, like if it is a global minimum, that is opposite way actually, that's fine. But I said, if I have a function that is a non-linear function, say if the error function is going like this, idiot. And now, if I would have started somewhere here, I will come down and then I will land up here and I'll tell this is my solution actually. Because this x-axis is a weight vector. I blindly started with some value and then I'm going to tell. I'll get stuck in this particular local minima actually. And also here, this particular gradient descent, when it has to learn, it will take small steps at a time and then it goes actually. For this diagram which you are seeing here, this should be my objective. I should try to find this solution actually, not this one actually. But it cannot guarantee that one actually for us. And also, it goes a small steps one by one, and then try to find actually. That is, if the, 1 minute, if the error surface is elliptical value, it zigzags and then converges slowly. That is here, this diagram you can see. I started blindly with this value, which is here, and then go take a zigzag fashion, that is step by step, and then I will reach this particular minimum. Okay, I'll try to find this one. That is, when we go this one, any of gradient descent or conjugate gradient descent will not guarantee for the global minimum, but it tries to converge very slowly actually. But we will go with the conjugate gradient. Say in this diagram what you're seeing, I started here, my steps taking will be little faster, and then within a few iterations I can converge and find the minimum actually. That is the guarantee which the conjugate gradient can give us. That is, conjugate gradient descent is an optimization algorithm that finds the minimum of the function more efficiently than standard gradient descent. That is, gradient descent also will give me the function, give me the result, but it converges very slowly. But conjugate gradient descent also will, gradient descent will give me the result, but it converges very slowly. But conjugate gradient descent will also give me the result, but it will give me the result in a more efficient, that it will try to converge fast when compared to the gradient descent. This is the main difference between the gradient descent and then the conjugate gradient descent method. Now, we have to understand how actually the conjugate gradient descent will give more efficient results than the gradient descent. Uh, but uh, I will not be able to cover completely, but I'll give some introduction like what the conjugate gradient tries to do, and in the upcoming class I'll try to show the derivation and see how it converges. Now, to understand the conjugate gradient, we have to put some basic foundation with respect to the Taylor series. Maybe we would have studied in the engineering maths, but we'll recollect because based on this only we'll go forward in putting a foundation for the conjugate gradient. A Taylor series is a series expansion of a function about a point. A one-dimensional Taylor series is an expansion of a real function f of x about the point x equal to a. That is, for example, say we have updated the weight in the neural network now W. I am there. That is on like if we take somewhere, I am there here. I know my W is this one. Now I should stay. I should think about whether I have to take a step this side. I have to take a step this side. That is delta W. I should know actually whether we have to go this side or this side actually. Now, when I am this particular point, I'm thinking whether what step I have to take the delta of W so that I'll get the minimum error actually. At that time, we should know if I'm in this particular point, what is that I'm going to get if I'm going to take this one actually. That's why in the Taylor series, what it tells, a one-dimensional Taylor series is an expansion of a real function about the point x equal to a. That is here, this is my W and this is my delta W, what we are trying to do actually. That is, this a function f of x can be approximated around the point that is x equal to a with f of a, and this f dash is the first derivative of that particular function, and then x minus a, and then double second order derivative f double that is f double dash of a by 2 factorial and x minus a square. That is, this becomes now what? Second order function. That is, we can approximate this function with the uh, terms over this thing, like using a first order, second order, and third order, and we can keep going like this actually, and then we can approximate this particular function. That is the why the Taylor series has been. That is, I can, if I want to know the value of this x, value of this function, x around the a, then I can compute like this actually, and then put the value of the x and then find out what is the final value of the x when we are final value of the function around the x for the a. Now, this is just a simple explanation of the Taylor series. Same thing, we now take it for our this thing, the neural networks and the weights. Say what I said, we know currently our weight vector is W of n. Now we have to update this by delta of W of n. Now, but we have to update in such a way that my average error is going to become lesser. That is, EAV of W denotes the cost function and average error over the training sample. That is, using Taylor series, now we'll expand. This is x plus y. And we have to expand this function using the Taylor series. That is, now when we have to expand, what I said, first is a function, that is f of x, what we call. So, and next, this is the first derivative of that particular function, first derivative, g. G here you can observe here actually. It is first derivative, average error, that is derivative of the average error over the W. And we currently know that it is getting evaluated for the value W equal to Wn. And in the Taylor series, if there is more than one term, this becomes a transpose here. This is a derivative, but it becomes transpose because we have to get multiplied with this particular. This is a vector once again. That is delta of W of n. And next term is a second order derivative. Second order derivative will be indicated by the SEN matrix because we have seen that one, SEN matrix. Because what the SEN matrix tells, like we have to find with respect to a function with two variables, x1 and x2. what it tells, SN matrix, first we will find the derivative of x1 with respect to x1 and then x1 with respect to, x2 with respect to x1. And next it will be the x2 with respect to uh, 1. I think I'm going in the opposite. Maybe it will be, okay, x2 only we will take. I should interchange this one. X2 with respect to the, I got it. X1 with respect to x2 and x2 with x2. That is a combination of all this one. That is, there are two variables, x1 and x2. My SCN matrix will be partial derivative of the x1 with respect to x1 and x2 with respect to the x1 in the first row, and in the second row x1 with respect to x2 and x2 with respect to the weight. Because if there are two weights, W1 and W2, we want to find the rate of change of W1 with respect to W2 and similarly W2 with respect to the W1. That is, when we go with the second order term in our Taylor series, this becomes an SCN matrix because more than one this thing weight vectors will be weight values will be there, and we have to find all that one. Therefore, we give the SCN matrix here. And now the matrix H of n is the local SCN representing the curvature. We have to understand the difference between, that is, this first order derivatives always will give the information about the slope. Second order derivatives, when we go, it will give the information about the curvature. That is, if I take a function like this, correct, I'll take the other color. In this point, I know what is the slope. Whether I'm sliding down or sliding up, I'll be knowing it. That's fine actually. I can come to know actually. But when I'm here actually, I should know whether my curvature is going to move up or bottom actually. Because this is the like curvature up actually. But if I'm here actually, this is a curvature down actually. Curvature down actually. And this is curvature up actually. If we go with the first order derivative, I'll be knowing the information about only the slope, but I'll not be knowing the information about the curvature. Therefore, when we use the Taylor series, we use the second order term to know the information about the curvature of that particular function. Therefore, we go with the SN matrix because I'm here. I should know whether I am in this thing curvature down or curvature up, because at that time I can make more quicker decisions instead of just getting stuck in the local minimum. That is, what is the point we are trying to understand here is in this slide. That is, I'll discard and I'll explain once again. That is, this function is Taylor expansion for the weight vectors with W of n and delta of W of n. This is a function itself, because until now we have used this one, that is rate of change of error with respect to the weight, what we have done. But after that we went with the first derivative. That is, we have used this first derivative in the gradient descent algorithm, because that is what we did. And that when we go with this one, it will try to capture only the slope. But if we go with the second order term, in the Taylor series, it will try to capture the curvature information of my function, that is a function, the loss function, so that I can get better results. That's why we go with this particular second order term in the conjugate gradient. That's why I wanted to put the foundation this one, because we use the second order term, and also sometimes we call this as a quadratic term. We call this as a quadratic term, because in the gradient descent we have used only the first order term. Up to this particular point we have used the slope, but we have not used the curvature actually. Therefore, we go with the conjugate gradient and make use of the second order term and then proceed further. That's what I said. that is this function, that is this was up to here was the gradient descent for me, and this I said that is updating the weight is by negative gradient, that is the learning rate, and g of n is the gradient, that is rate of error, rate of change of error with respect to the weight when it is a steep gradient, steep descent method or the gradient descent method. But now in the conjugate gradient descent method, we are going to use this quadratic term. That is, in order to produce a significant improvement in convergence performance of multi-layer perceptron when compared with the backpropagation learning, because we have studied until now backpropagation learning, we have to use the higher order information in the training process. This higher order information is my second order term which I have to use actually. We may do so by invoking the quadratic approximation of the error surface around the current point W of n. That is what we will use actually. That is, we will be now doing in the conjugate gradient, we will be going with the quadratic approximation or the second order term approximation, or the higher order term, higher order information will be used during the training process. Now, in the what the conjugate, that is our aim is this one, quadratic that is quadratic approximation we have to do, and we have to make use of this particular higher order terms along with this also actually. But we will look at in general what is conjugate gradient actually. What the conjugate gradient method is going to do is it tries to solve this equation Ax equal to b, where A is the n cross n matrix, X is the unknown vector, and B is the known vector. That is, our unknown vector is what? The weight vectors. And our known, this n cross n is what? That is, we have the input actually with us. And known vector, that is output, is also known to us actually. But we will not be, we don't know what is the weight vectors we have to put actually. Therefore, it is something like relatable actually to the neural network what we have studied. That is, A is a matrix which has been known for us actually, and X is unknown, and B is the known actually. And now in the conjugate gradient, we will try to solve this one so that we can get the solution for this one. But here there is assumptions. That is, this n cross n A matrix, we will consider that it is a symmetric actually. Symmetric in the sense A transpose is equal to A. And it is a positive definite in the sense that is X transpose A with X is greater than 0 for all non-zero vectors, that is X is coming from the input here actually, that is R of n and real, but B is also known actually. Now we have to find the solution for this equation, that is X actually. Now, finding the solution for this equation, our objective is what? We have to find the solution for this equation, that is a X value. This one, instead of solving this equation directly to find the value of the X, we can go in the other way around, where we can minimize f of X equal to 1 by 2 X transpose A multiplied with X minus B transpose of X. See, our objective is to solve this equation so that we can find the value for the X. But now instead of directly solving this Ax equal to B to find the solution for X, we will try to minimize this one and find the solution for the X. As I said, A is an n cross n symmetric positive definite matrix. X is an n-dimensional vector and B is a constant. And now when we take the second order term, which I said actually, it will become a quadratic ball format. We are indirectly trying to find the X value by trying to minimize this particular function. That is, to minimize f of X, which is being given here, we compute its gradient and set it to 0. That is gradient of f of X. That is, this is f of X, the gradient, this is that is f dash of X. and then we have to make it to ax minus b actually. I'll tell why we are getting this ax minus b. Now you this from this particular function you take the gradient, in the sense derivative. When I try to take the derivative, actually the two will get cancelled. This is a transpose that will get cancelled, and I'll get this a and then the x. That is, derivative of this term will become ax, and derivative of b transpose x will become b, because we are deriving with respect to the x here also and x here also. Now what that is this we have to get ax and then b actually. Therefore, so this particular term, that is ax, because already we had here the minus here, therefore ax minus b it becomes. Anyhow, I'll make it clear in the next slide, but this is what we are trying to get actually, the point here actually, that is taking the derivative of this minimization function and showing that that is equivalent to ax minus b. That is, when we do this one, we are getting this one, and then we are setting this derivative equal to 0. But now when we set this derivative equal to 0, and I said that we will consider this as ax minus b actually, because you didn't have the clarity why your minus was coming at. But if I make this as ax minus b equal to 0, and then ultimately what I'll get ax equal to b, because we have to solve the equation ax equal to b and find the solution for this particular x actually. That was a, but we are going in the other way around, where we are going to minimize this one. But now when I take the derivative of this f of x actually, I can show that this derivative of f of x is going to become equivalent to ax equal to bh. Therefore, we can try to minimize this f of x to find the solution of the function f of x. That is, minimizing f of x is equivalent to solving ax equal to b. The point where the quadratic function reaches its minimum is exactly the solution of the linear system. Now, as I said, in conjugate gradient, uh, uh, we, we can solve this equation directly. But when we solve this equation directly, it is expensive, because it is a matrix here and then here, and then we have to find it. If the system is large, it becomes very expensive. But we will go in the other way around, where we will minimize this function with this one, that is, minimum of f of x is 1 by x, x transpose a x, and minus b transpose x actually. And now to minimize this one, we will be using the optimization methods like conjugate gradient descent methods or quasi-Newton methods, because I have to find the minimum of this particular function. That is, these methods move toward the minimum of the quadratic function, which automatically gives the solution of ax equal to b. Now, what we are trying to do, summarizing, is our aim is that is ax equal to b can be solved by minimizing this function, because derivative of f of x can be given as ax minus b. And now when we equate this to 0, it becomes ax equal to b. That's the main point. And now to closing, further I'll continue with the conjugate gradient, because some more derivations are there. But to show you the difference between the, because we had the optimization method, that is gradient descent. There is no doubt in that one actually. But now we are going with the other optimization method, that is a conjugate gradient method, because we want to get more efficient and in a quick manner the result actually. This diagram, what you are seeing is both conjugate gradient and gradient descent started at this particular point. That is, my uh, gradient descent is going a step like this, going like this, going like this, and then going here, and then trying to find the minimum. But when you observe this conjugate gradient, what it is trying to do, it started here once again, but it took this step and then it took this one, and it was able to converge little faster when compared to the gradient descent. That is, convergence will be little faster when by the conjugate gradient when compared to the gradient descent. That's why sometimes we use the conjugate gradient descent in the optimization.